Well, good evening, everybody, and really nice to talk with you. You already discovered I have a funny accent, but I'm actually a Kiwi, and I think I probably just destroyed my credibility by saying that. But I was born in Chicago, left when I was 7, and came back with a speech impediment at age 22, and haven't been able to shake it ever since. So that was just a couple of years ago, of course. And here you see me doing my David Bellamy imitation. This is a banyan tree that I saw today, really cool. So where is he? Where's Ben? This man over here is responsible for sneaking this through customs, as I understand it. Nobody here from customs, are there? Okay, good. So he says, yeah. Okay, so of course this isn't one of our NZDFI species, but it's just all of us who are in this program, we share a passion for trees, and so that's part of my passion to appear like David Bellamy. What I'd like to talk about tonight is what we're doing to help with decision making, particularly people who are interested in planting these species on their own properties. So we'd like to help you determine which are the best species to grow in your particular property at a micro level. We'd like you to be aware of the risks. We'd also like to provide systems that enable you to get some idea of the productivity of these species. And let's show you an example of a system that it's been around for a while now. It's originally a Sustainable Farming Fund program. And this enables you to go onto the website, and you can bring up a map. You can point where you are on the map, and it will bring in some information underlying Google Maps. And you can see a lot of information there. Does this pointer actually work? Anyway, all the information along the right-hand side there. That is some of the best that we have from our layers at the moment of features across New Zealand. And you can bring those through into a decision support system and click the Go button, and it'll give you a list of species, and it'll rank them, and it'll tell you more about why it's ranked them, their productivity, the extent to which they're limited by cold, their water limitations, carbon sequestration. You also see a few graphs there to give you some idea of what's underneath the hood of this little package. It's a combination of an ecophysiological model that's founded in tree physiology, plus practical but flexible rules based on interviewing people who really know about trees and binding those two things together into a decision framework. And so it's ranked the species, and not everybody would necessarily agree that radiata pine should be the top in this case. But it's giving you the maximum minimum temperatures across the years. It's giving you the results of a water balance model in that lower graph. In the system, you can look at whether it's even financially feasible to a certain extent, and then it gives you some idea of the cost of harvesting, given your land, if you wish. And it'll tell you why it didn't choose other species. It'll list the rules that were violated, and so you can get an idea of what's happening. It also gives you an idea of whether you're likely to have a wilding problem. So we'd like to have our NZDFI species in this framework, and we need to do quite a lot of work to get them there. And we also like to have models like this that where you can look at future production. If you know the tree sizes at a certain point in time, you can grow them on and see what they're likely to be at a later point in time. We'd like to have models like this as showing basal area growth through time for radiata pine in Canterbury. But, and here's a distribution of tree sizes that we can plot through time in this modeling framework. We'd like to have this sort of thing for our NZDFI species. So in addition, we'd like to be able to produce this kind of map. And this is a fairly low resolution version. This is a point every 800 meters. It's not a high enough resolution for your purposes, in my view. But this shows radiata pine productivity. It's redder. It's more productive. If it's white, it's not going to grow. And not only that, this system can tell you why. So redder, more temperature limited. Redder in this case, more water limited. VPD limited. And fertility. We're still working on the fertility model in this system. Now, we can do this at 800 by 800 meters. We want to develop it, and we are developing it to the point where we can give you a 15 by 15 meter grid across a landscape. So then you're really cooking with gas. And when we do that, we need to understand not just the general flatland kind of productivity, we need to understand more about what happens with different aspects and slopes, which we all know are important. We all have stories about aspects. We all have stories about slopes. I heard them today, people saying Muellerina should only be put on a certain aspect. I'm sure Globoidia wouldn't have had that limitation, but you know, I know there's a bit of tension between those who think we should have Muellerina or Globoidia, so I'm just feeding into that tension here. You know, that kind of thing you hear all the time, and the question is why? What's going on? And can we understand it from a scientific point of view, from an ecophysiological point of view, and bring that into our frameworks for decision making? Now, just to give you a little idea, just a little bit of peek under the hood. I'm not going to pull the engine apart and show you the innards. Just a little peek under the hood of this kind of thing. This is one of the aspects of this sort of system where we understand the relationship between temperature and photosynthetic activity, and we've been exploring this for some of the NZDFI species. And so it's temperature along the bottom there changes, the rate of photosynthesis changes. And we reach to an optimum, then a decline. Now, the main reason for the decline is because the trees, once they get too warm, they start to respire so much, the respiration overwhelms the photosynthetic rate. That's the primary reason for that drop over. There are other reasons as well. But, and don't worry about the 3 different colors, that's too much pulling the engine apart. So we'll continue. So one important question is, if we're going to drive this sort of system, how can we get good input data to drive it at a very high resolution? So we have our National Institute of Water and Atmospheric Research, and clearly some of their information is very important. To have local estimates of rainfall, to have local estimates of temperature, radiation, and those sorts of things that drive our trees as they drives the tree growth. So as part of the NZDFI program, we've established some meteorological stations and parts of other programs as well, and we've got 9 stations that are independent of NIWA. And it gives us an opportunity to say, well, how can we localize what we can get out of NIWA and make it relevant to a specific point in the landscape rather than just being a NIWA Met station or part of a fairly coarse NIWA grid. So I looked at how the data from these stations related to what we could get from the closest Met station, NIWA, for any given variable. And some variables are far more localizable than others, as you'll see. Some are, have many more stations than others. For good reason, as you'll see. Every day, you may not be aware of this, but every day, NIWA does a calculation and creates a new surface across New Zealand of what's happened with the weather that day on a 5 by 5 kilometer grid. And you can get those layers going back to 1980, right? So that's a pretty phenomenal amount of information we can get about sites across New Zealand. And so that's called the VCSN, Virtual Climate Station Network. And here are the grid points across a part of New Zealand. So every 5 by 5 kilometers. So is that information useful to us to get down to a final level of resolution than 5 by 5 kilometers? That's the question. So what I did was I took these 9 stations and I looked for the nearest grid point. So the stations are in red, the VCSN points are in blue. And I started to look at across months of data with monthly averages, how they compared. And so here's radiation. And even though the radiation stations in New Zealand are quite widely dispersed, there's a pretty good match between what we observed in our points in the landscape for radiation and what we could get out of the nearest VCSN point. And they're saying pretty much the same thing. There's a little bit of bias, so the stations are different colors and different symbols. And you can see that the stations aren't completely mingled with each other, but for our purposes, it's a pretty good estimate of what's going on at any single point in the landscape. For temperature correlations, if we take raw VCSN, we get, now an R value of 1 means an absolute perfect match between our measurements and what NIWA is saying. 0 means there's no match. And so if you're getting up towards 1, it's a pretty good match. So we're looking at raw VCSN, 0.97 correlations. These are R values. If we adjust for the elevation of the grid point versus the actual elevation of our station, with a lapse calculation, we can take that to 0.98, or we could do what I call a Norton. It's after David Norton, who works at the school. It takes into account not just the lapse rate, but also distance from the sea and the latitude. We can do it. It's pretty similar for the VCSN points. Once you start taking the closest Met stations into account, Norton adjustment is better than a simple lapse adjustment. And so, for instance, here is average monthly average daily maximum temperature from the lapsed VCSN against our station. It's the same variable. So you can see, again, there's some bias with station, but it's usually within about a degree or sometimes 2 degrees, somewhere in that range. Not too bad for monthly average. This is minimum temperature, which is a lot more variable, much harder to localize, but still not too bad. We have problems with this, and it's interesting that there are far more stations across New Zealand from NIWA that are measuring rainfall than there are that are measuring temperature. And there are far more temperature stations than there are radiation stations. And you can see in our data why that is. We don't have great correlations between what even the VCSN points say should be falling on our land and what's actually falling on our land in any given month. And that's a limitation. And so we'll talk about that in a minute, about what that means for our modeling. But it's important, particularly obviously in dry lands. It's very important. There's also an issue with the layers that describe our soils. And this is the results of a small study by a student named Malte Kuhlmann, who a few years ago undertook to look at what the geographical information system layers were saying about plant available water and what that implied about rooting depth, given the soil type, and where the roots actually were. So here I've plotted it as our measured plant available water in soils that were being used by the Salmon Plantation Board in Canterbury, and reported plant available water. And you can see that generally there's an underestimate by the layers. What that means is if you're using those layers to simulate tree growth, we're using any kind of ecophysiological model, it doesn't matter if it's 3PG or Kabbalah or SENW or any of those biomass Gaudet model, the trees that are being simulated will dry out before the real ones do, right? That's what this means. And so we need to be aware of that and make some adjustments for that in our models if we're going to try to make the models realistic. So the implications are that the VCSN estimates are better than those from the nearest Met station for all variables, that radiation is well estimated at specific points in the landscape, and we can localize those really well. Temperature can be localized using adiabatic or Norton adjustments, and I prefer the Norton adjustments because I think they're just slightly better. The dry areas are likely to have more biased estimates of productivity than wet areas in our landscapes, which is unfortunate. I mean, you may have, you'd be well within your rights to think after today, this is not a dryland forestry program, but it is, right? We're going to be looking at dryland species. And so that's an issue for us, and it's something we need to work on. And it's an issue for anybody who's trying to estimate productivity using any kind of an ecophysiological approach in New Zealand. So rainfall is very local, and it's roughly estimated even by the Virtual Climate Station Network. Maximum available soil water is within the root zone is also very poorly estimated within our national information systems. Now, in addition, we want to look at slope and aspect. As I said, everybody has a story about aspect, right? All those who are involved in growing things will have stories about aspects. And in our minds, we imagine what's going on when we talk about aspects. Some people think it's probably radiation. Other people say, well, it could be soils. It could be temperature. There are a whole variety of stories associated with that, but it's anecdotal. And there's surprisingly little work done on this in the scientific literature. And we want to start doing some science with it. So this is one of our DFI sites, and that's Globoidea. If it were Mulleriana, would it be worse than that? I don't know. Probably no trees left at all, right? No, just kidding. Okay. So anyway, this shows clearly that slope and aspect is affecting tree growth on this site. Now, I apologize for this, and I might have to duck here because I'm going to show you some radiac pine. But here's another example of where location in the landscape over a very short distance can change productivity. And as I said, we all have stories about these things, so the question is, what's actually really going on here? What is happening? And can we capture that in a modeling system to make decisions about it? Here's an example from one of the NZDFI sites. This is on a northerly slope, and you can see a fine gentleman there standing, showing how big the trees are. They would have been about 1.5 years old, maybe 1 year old at this stage. Yeah.
Where is that site?
That's Lawson.
Oh, okay.
Yeah. So that's the northern face of Lawson. Here's the same age, eastern face, right? Just around the corner, sort of 30, 40 meters away. Yeah, okay. So we're looking at impacts of slope and aspect, and I've developed some software that will give us, on any aspect, anywhere on Earth, for any slope, will give us the change from the difference between flat ground radiation and aspect radiation at any time of year, right? So that's going to influence temperature, but if you look in the literature, nobody has figured out what that means for temperature in a systematic way. So we have on soils, we have a study underway with a PhD student, comprehensive soil survey data on 2 sites, looking at aspect and slope, and also distance from the top of the slope and or the bottom of the slope, which is relevant for this kind of work. To give you an example of this, how the software can work, if you know the radiation coming in each month, this is real radiation measurements from Canterbury from one of my experiments on a flat site, and that's the maximum temperature profile over 12 years. And if you say, well, what would happen on the site if you had a north aspect 25-degree slope through those months, and what's on the y-axis here is the proportion of flat ground radiation that you're seeing on the slope. And you can see that the biggest impacts of this northerly aspect, if it existed, would be in the tail ends of the beginning and the ends of the seasons. And in the middle of the season, you actually get less radiation on the northern slope than you get in flat ground, right? Because the sun rises behind the hill, right? So, and this is not just geometric, it also takes into account the proportions of diffuse and direct radiation. That's why you need the maximum temperature. If you look at a southerly aspect in the same site, 15-degree slope, you never get as much radiation as you get on flat ground. And again, but the biggest effects are at the beginning and the end of the season. So the message here is a northerly aspect is possibly extending your growing season, and in particular ways, in ways that we can describe mathematically with this software. If we look at the maximum temperature against NIWA station radiation from the data set I used for validation of the stations, or the station validation of the network, you can see a rough line there that says that with more radiation you should have a higher temperature, but locally this won't work. This is across widely dispersed landscapes. In local areas you get airflow between aspects, and so the slope is going to be lower. And the question is how much lower? And to what extent does wind affect that? So we've got some work looking at that. We've got zones where we put in a whole lot of temperature loggers and also soil moisture loggers, and we're doing soil surveys on different aspects and slopes on NZDFI sites. And here are a couple of really cheap loggers, wonderful to live in the modern world, when for less than $100 you can put out something that will measure temperature every half hour for 3 years and store the data for you without you having to worry about it. Here's another site, Lawson's. We're doing the same thing. Saggers, and just put some out on Ben's sites today. Yep. So the key points are we're making some decision-making tools to help you with your decision-making about what species to grow and what their growth and yield is likely to be, what sort of products you would have at the end, ultimately is where we want to be. How much heartwood you're going to get and when. The studies are underway. We want to know how to localize the important variables that drive the system. We want to look at microsite variation with aspect, slope, and soils, and look at landscape level productivity, but at very, very high resolution. So you can point at your particular paddock, portion of your paddock, and you'll say, on that place there, you should probably grow this species. And it's likely to grow at this sort of rate. And the software is under development. So that's it. Thank you.